Good day. For those of you who do not know me, my name is Douglas Harder, and in this topic we're going to discuss approximating solutions to systems of higher order initial value problems. So in this topic, we will discuss how to convert a system of higher order initial value problems into a system of first order initial value problems. We're going to look at one concrete example, which is a system of two second order initial value problems, and then we'll look at a more abstract case. However, most of this topic is simply demonstration by example. The purpose of this talk is to understand how to approximate a solution to a system of higher order initial value problems. We're simply going to do this by example. So here we have two second order initial value problems. Now, this consequently requires four initial conditions. We have a second derivative of the function y, therefore we need both the initial value and the initial slope of the solution y, and the function z also has a second derivative, therefore we require two initial conditions for z, again the initial position and the initial slope. This is for some time t naught, usually 0. So now the unknowns will be all the lower derivatives other than the highest derivative of each of the functions. So in this case, there's y and y prime, as well as z and z prime. So we will let the unknown functions w0, w1, w2, w3 represent these in order. All right, so now we have four functions w0 through w3. We can immediately translate the initial conditions. Recall that the initial conditions were for the functions y, y prime, z, and z prime. Well, if w0 is y, then w0 at time t naught is y naught. And the same for w1 being the derivative at the initial time of the function y. w2 at the initial time is z0, and w3 at the initial time is the slope of z at the initial time. Now we also note that if we differentiate w0, well, w0 is y of t, therefore w0's derivative is y prime, but we were representing y prime by w1. Therefore the derivative of w0 is w1. Similarly, the derivative of w2 is w3. That leaves us with determining what w1 and w3 prime are. Well, let's take the two ordinary differential equations, and let's move everything to the right-hand side except for the highest derivative. Now, again, according to the implicit function theorem, this should be almost universally possible. However, we're going to look at more simple cases where we don't have to apply the implicit function theorem, such as these. All right, so on the left-hand side, we have the second derivative of y is the derivative of the derivative of y, which is the derivative of w1. On the right-hand side, we have the derivative of y, which is w1, y of t, which is w0, and z, which is w1. And the same for the second. So making all the appropriate substitutions, notice now we have the derivative of w1 is an expression in w0, w1, and w2. It could also be of w3, but that's not the case here. W3 prime is also in terms of the w functions. Thus, we have the following. As a vector, valued function, the derivative of the vector w is simply given by the right-hand side, and the initial condition is given by the initial values of y, its slope, z, and its slope, all at time t0. We can write the left-hand function in our format. So we have a function that takes a double and a vector, four-dimensional, as arguments, and it returns a four-dimensional vector. As you can see up here, w1, then standard sine of t minus that linear combination of the w values, and so on and so forth. Now, we can immediately put this into our dp45 function, and we'll get a solution. In fact, this does actually have an exact solution which you can find in a symbolic programming language such as Maple. However, here we see the solutions to y of t in red and z of t in blue, and the approximations found by dp45. All right, but what is the output of dp45? Recall that the output of dp45 is a tuple of four entries, so a quadruple. The first one is the number of intervals, so the number of points plus 1. The second is an array of as many t-values, so all the t-values at which we approximated a solution. Notice that the initial step size was 0.1, then it doubled again, and again, and again, and again, and again, until it was of an appropriate size for this problem. The third object returned in the tuple is an array of vectors. Each vector is four-dimensional, and the first entry of the vector is the value or the approximation of w0 at the given or at the corresponding t value. But recall that w0 is y of t. So therefore the first column gives the approximations of y of t at the given t values in that first column. w1 was a derivative of t, so this would simply give the derivative of y of t. The third column, w2 of t, represented z of t, and thus the third column represents the approximations of z of t at the corresponding t values, and finally the last column are the derivatives of z of t. Now, the next column, there is actually a fourth tuple, but that is simply the derivatives of each of these functions, or at least the approximations thereunto. As another example, a little more abstract, suppose we had four coupled ODEs. The first, fourth order, the second and third are both second order, and the last is third order. Consequently, we would require 4 plus 2 plus 2 plus 3 initial conditions. These initial conditions would have to be satisfied. Additionally, we would be converting this system of four higher order initial value problems into 4 plus 2 plus 2 plus 3, or 11 first order initial value problems. So, for example, the successively higher derivatives of the first function would be represented by w0 through w3. The derivative and the second function and its derivative would be represented by w4 and 5. The third function and its derivative would be represented by 6 and 7. and the last function, its derivative and its second derivative would be represented by W8, W9, and W10. We can then calculate the derivatives of each of these and see that they correspond to appropriate values. We would therefore also have equivalent initial conditions for this W function. Following this topic, you now understand how to convert a system of higher order initial value problems into a system of first order initial value problems. You have also seen an example and its solution. Here are the references, acknowledgements, the colophon, and a disclaimer. Cheers!